So hello everyone. In the last session, we are seeing about the conductors. So let us proceed with this session. In this session, we will go to the derivation and let's see what are the formulas for it. And one more thing, there is a one mistake I did in writing the thing. Yeah, here I have written ground. That should be acceleration. It will not be ground because I given the explanation correct, but I while writing I written as a ground. Okay, so just correct this. Okay, but when you will get this PPT, it will be corrected only. That is not an issue. But yeah, this should be acceleration. If there is any mistake I did while writing, just please tell me in the comment box. And we have also a WhatsApp group which is present on the channel link. You can join that group, and if any type of suggestions you want to give, you can give through that, so that we can correct the things, because I am also a human. So there are some while writing I can make the mistake. While telling the concept, there is no mistake. While writing, there may be a chance. Okay. So I given you the conclusion basically about the conductor. So let me write it so that you can get a better picture once again. So basically what I told you, that we have a spheres. We have to discuss about the spheres. In spheres we have a, basically I am concluding the study thing in different manner. We have a two cases are there. Okay. One is a conducting. If we see, one we have a conducting, and another we have a non-conducting. Okay, just I am concluding the last lecture only in another manner, continuation of the last thing. Okay, continuation. Yeah, conducting and non-conducting. In conducting we have a two case. One is the hollow. Hollow means it is inside, there is no material. That is a one case. And there will be another case, that is solid. Okay, similarly in non-conducting we have also again hollow. Another we have a solid. And we have seen that the properties, the charge distribution in these three cases, what we have seen, in all these three cases, they are same. They are same in inside and outside. Whatever position you will take, they have a same properties and everything is same. That is the same thing. Similarly for solid one, if you talk about for solid, what we have seen, that they are, it is a different, it's different. So basically we can say our whole thing is going to be divided into two parts. Okay, we have to see this one part and this another part. Okay, so that is why whatever the formula I will derive for this one, the same is applicable for this also, and same is applicable for this also. Okay, give me 1 minute. Yeah, so yeah, it is the different case. That is a overall conclusion which I am trying to give you in the study session. Now let us start with this. Correct. So basically, let us start. So first I am going to take the basically conductor. In conductor I am doing the derivation on like on side by side, so that be more clear for you. Okay, and try to remember the formula, because it is very important part. and it is a favorite part of what happened. Okay. Yeah. Our first case I am going to do, I am taking the conductor in, we have two cases I told you, one is hollow, one is solid. First I am taking hollow one. Okay, so hollow conductor. Okay, so if it is hollow conductor, you can tell me one thing, sir, whatever the charge will be there, the charge will be only present on the surface. It is a hollow, remember it is a sphere, not a circle. So suppose the radius is r, and if we give the charge q, obviously it will be distributed on the surface. So here we have to take lambda, sigma or rho. You tell. Obviously sigma, that is coulomb per meter square. And why? And this sigma will be uniformly distributed. Why? Because why it is uniform? Because the radius of curvature is same everywhere. There is a reason for it. Okay, it is not always uniformly distributed. Okay, now this is there. Now we have to find the electric field. So basically, first our aim is to determine what thing? First electric field, then potential, and then potential energy. That is the three things we have to find. Okay, so what I am going to do? First I will find the electric field. For the electric field, there are the two cases. One is R is less than R. Okay, our first derivation is going for R is less than R. That is the first case. If this is the case, I will do E dot dA, correct? E dot dA is equal to, by Coulomb's law, into Q inside by epsilon naught. I have to take a one Gaussian surface just inside. Suppose I am taking a Gaussian surface just inside, this distance is small r, so obviously the q in is 0, so my electric field inside will be how much? 0, or I can say a point A or point B. So I can say my internal electric field, inside electric field will be 0, and that we also know, because in conductor inside electric field is always 0. Now the second case is r greater than capital R, means outside the conductor. Suppose this point. Okay, so for this point I will take another Gaussian surface like this. Are you getting my point? This is my another Gaussian surface. So here I will write integral E dot dA is equal to q in by epsilon naught. Now first you tell me what is the total charge inside. That will be capital Q, correct? Now what, obviously this thing we have done here, the dA vector will be like this, E vector, they both are in the same direction, and E is constant everywhere. So I can directly say E into 4 pi r square. I am not writing these steps, we have done lot of time. So 4 pi r square. Okay, that is my like distance I am taking. This is my distance from center, that is small r. So from here I will get my electric field as how much? How much is the electric field you will get? That is q upon 4 pi epsilon naught into r square, correct? If you see this charge, this is a electric field due to a point charge. So basically this whole charge will go into the center. So that is our first thing, that is the electric field. Our first derivation regarding electric field. Now our second case is magnetic field. Second case is not magnetic field. Second case we are going to see the what? That is potential. Second thing we are going to see is the potential. Potential. In potential, what we are going to do? Let's see here. First case we will again how to find the potential. See, where we have very simple formula, that is integral dV is equal to minus E dot dr, correct? Now we know if we are talking about r less than r, then we can say my E is 0, E inside is 0, correct? So I can say my integral dV will be what? 0. So from here I can say my V final is equal to V initial. Now we have to choose which is my final, which is my initial. So my final, we are basically going from center to surface. That is the limit we have. So obviously I can say from here my potential at the surface, whatever the potential at the surface, that will be same potential at inside also. Means the potential inside and the potential surface both are same. That is a conclusion from here. Now the second thing, if you remember in the property of conductor, I told you whatever is the potential inside, that will be the same potential at the surface, and from here we are getting the reason for it. Now similarly, for r greater than capital R, if you see, then integral dV is equal to minus E dot dr, correct? Means we are going from, we want to go to up to infinity and we want to measure the potential. So how we can do? How we can measure the potential for this? What is the approach? What the approach I will use? So I will simply, what I will do, I will take, I will write the electric field first. E dot dr will be obviously 0, correct? E dot dr will be 0 because electric field in this direction, dr vector we will also take in this direction. So electric field is, we got 1 upon 4 pi epsilon naught into r square, correct? Then there is integral, okay, into dr vector, okay, integration, minus sign is there, integral dv. Now we are coming from infinity to r. From infinity I am going to small r. That is our case. And at infinity the potential is 0, that we know, and at some point the potential is, we want to find is Vr. So basically from here what we will get, that is 0 to Vr is equal to V, and that we will get as Q upon, Q upon, and it will be, integration is 4 pi epsilon naught, and the limit if you will put, you will get 1 by upon 1 upon infinity. So from here you will get potential at distance r outside, this is outside point, 4 pi epsilon naught into 1 by r. So from here you get the potential at any point is this much. So what, so if I ask you what is the potential at surface, capital R, so it will be simply Q upon 4 pi epsilon naught into capital R. So from here can you tell me what will be the potential inside then? And inside potential will be kq by r, sorry, kq by capital R. So that is the formula. Basically what is the conclusion you have to draw? The conclusion is very simple. Conclusion is very simple. Suppose, because this thing you have to remember, and along with the derivation, okay, because why derivation is important I will tell you when I will give you a question. Suppose this is my what, sphere, and it can be three things, and in conclusion what you have to remember, it can be three things. What are the three things? It can be hollow conductor, correct? It can be solid conductor, and it can be hollow non-conductor. Because in all the cases the charge will be always present on where? Surface, in all the cases. In all three cases the charge will be always present on the surface, that is always true. Okay, the charge will be always present on the surface, always. If it is like this, suppose the charge is q, then there we have to find the three things we have. First is, suppose this is my center and this, the radius is r. Then we have a two cases, that is inside point and outside point. We have two cases, inside point and outside point. Sorry, inside point and outside point, that is r less than capital R and r greater than equal to capital R. If you want you can put, no issue. So what is the thing we have got? First, r less than means inside point. When my r is less than capital R, that means inside I am talking about. This is what? This is inside. So inside what we have to first find? First is the electric field. So what is the electric field we have got inside? I am directly writing E only. Okay, E vector we have got is equal to 0, means there is no electric field inside. First thing. Second thing, what is the potential? Potential inside we have got, that is potential at the surface, that is kq by r. So that is the two thing. There is a one more thing is there, potential energy, that we will discuss later. What is a potential energy? That we will discuss later. Right now I am not mentioning. Okay. Outside. For outside point, how to find? Okay, for outside, see, E vector what we have got? We have got E vector as k q by small r square. That is the electric field due to the, that is the electric field due to the r greater than capital R. And the second is potential. Potential at any distance r outside point will be k q by. So that is the conclusion we have to remember. Ki this sphere can be any of these things, but whatever I have mentioned, it can be hollow conductor, it can be solid conductor, or it can be a hollow non-conductor. Because in all three cases, if you see, the charge distribution is same. In all three cases the charge distribution will be same, so their formulas will be also same. So internal electric field will be 0, potential will be kq by capital R, that is a constant value. If you see, this is a constant value, and I have told you this earlier also. And similarly, we have seen the potential will be like this, correct? So if someone asks me to draw the graph, okay, to draw the graph, yes. So that is the thing we got. Now if someone asks me to draw the graph, there are the two famous graphs are there, okay. Let's see these graphs. First graph, not straight. First our graph will be, what happened? So our first graph will be electric field versus R, and our second graph will be, that is potential versus R. That is the two graphs we have in our syllabus, potential versus R. So what we have seen that, you see the electric field inside is 0, means what we have get at R is equal to capital R, the electric field is 0, and as my R reaches the capital R, the potential electric field start decreasing, because electric field become inversely proportional to R square, correct? So that is the thing. So what is the surface? If I ask you at surface what will be the electric field, so obviously it is kq by capital R square, correct? Similarly here also, if you will see the inside, it will be a constant value. When R, as R become capital equal to capital R, it will be start decreasing. That means my potential is inversely proportional to R. And here what is the potential? That is kq by capital R. I hope it is clear now. So this is how the potential vary with the distance, and this thing will be valid for all these three cases. I hope it will be clear. Is it clear for you, or anyone have a doubt in this also? Is it clear? Okay. So we can now, so picture should be clear in your mind properly. Okay, the picture should be very much clear in your mind. Okay. Huh. Hmm. Okay. Clear till here. Shall I proceed further? Okay. So our next case is, what is our next case? Our next case is, what is our next case? It is again the same thing, but it is a now solid sphere, so obviously the charge will be inside. Okay, it is solid and also non-conducting. That is the only last case that is left. So we will see this case also. So it is a non-conducting solid. I have given everything. Radius is radius is r. So our aim and the charge is capital Q. Okay. Now our aim is to what to find? Our aim is to find the electric field inside, outside, and then potential. Clear? So first do the calculation of electric field. Okay. So first point is R less than capital R. Correct. So for R less than capital R, let's take a point for R less than capital R. Suppose this is my Gaussian surface. Okay. Suppose this is my Gaussian surface. Correct. Just treat it as a Gaussian surface. I am trying to bring. I am trying to do like it look like a Gaussian. So suppose it is my Gaussian surface, and suppose the radius of this Gaussian surface is small r. So according to Gauss law, E dot dA vector should be equal to Q inside by epsilon naught. Now here obviously we will take rho, that is coulomb per meter cube, because the charge is in the volume. Okay. So if I ask you what is my Q inside, can you tell me what will be my Q inside? Yes, the Q inside will be, I can say it will be, sir, rho into whatever is the volume of this Gaussian surface, that is 4 by 3 pi small r cube. Correct. Now here obviously the electric field will be constant, dA vector will be along, everything will be same, so I can write integral, what is dA vector, that is 4 pi small r square into Q value you will put rho into 4 by 3 pi small r cube by epsilon naught. So pi will cancel out, 4 will cancel out, r cube r square will cancel out. What is the value of electric field you will get? You will get the electric field value as rho r by 3 epsilon naught. And if you put the value of rho here, what is the value you will get? You will get Q r by 4 pi epsilon naught into capital R. That is the value you will get. Okay. That is a value you will, also you can write it as K Q R upon capital R Q. So basically, and what will be the direction? The direction will be along this, along the axis. Correct. The direction will be like this. Direction, finding direction is not a difficult. It will be along R vector. Na? Simple. So that thing is not a difficult task. But yeah, we got the electric field. That is the inside point, for inside point. Okay. Let me talk about for another case. What is another case? Now for R greater than equal to capital R. Now if we are talking about outside point, so we have to take another Gaussian surface which is present at outside. Correct. So let us take one more Gaussian surface which is present at outside. Okay. Suppose this is the Gaussian surface. Suppose this is the Gaussian surface. Suppose this is my Gaussian surface. Correct. And suppose the radius of this Gaussian surface is also capital R I am taking, and I am applying the Gauss law here. Close integration of E dot dA vector is equal to, that is Q in by epsilon. Now what is Q in? Q in is the total charge that is present inside. Yes or no? It is the total charge that is present in the total charge present inside is capital Q. So this will become, and obviously E dot dA, everything is valid. dA vector you will get 4 pi r square. Okay, that is Q by epsilon naught. So from here you will get electric field is equal to how much? K Q by r square. That is the electric field you will get. So what is the conclusion you have drawn? The conclusion I am writing here. Again I will write the final conclusion also, but let me do it here. Done. Let me write it here. A final conclusion for this electric field, what you have get. Conclusion we have got from here is that for r less than capital R, that is inside point, my electric field vector is how much? K Q R upon capital R cube, or this can be also written as in term of rho R by 3 epsilon naught, correct. Similarly, for R greater than capital R, how much electric field I will got? I got KQ by small r square. So this is the conclusion we have drawn from the whatever the thing we have did. But now let us talk about the next point, that is a very important, that is a potential. Okay. No need to draw any, basically we can directly find the potential for R less than capital R. We know integration, or let's first do for the external point. Okay, let's first do for the R greater than capital R. Okay, integration of dV is equal to minus E integration dot dr, correct. It is again same, we will go from infinity to some point R. Okay, some point R we are potential from infinity to some point R. We will go like that. What is the electric field we have got? We got again KQ by R square integration, that is from infinity to capital R, dot R into dr. This will be become V of R obviously. And what is this value will become? You will get KQ by, if you will solve, we will get KQ by R. That is a potential at any point R, which is where R is greater than equal to capital R. That is okay, no problem. But my question is that, and if I ask you what is the potential at the surface? Potential at the surface means capital R, that is KQ by capital R. That is again a constant value. Okay. Okay, that is okay. But the important part is now that the potential at, this is not very much important. The important thing is this is not that much important, but the important part is when R is greater than capital R, means for outside point, sorry, R is less than capital small r, means for outside point. Till here everyone note it down. First, do it fast. Completed? Okay. Now we are coming to this point. This is a very important part. See, we have to take R greater than less than equal to capital R. Okay. If you want, you can remove or add, but we are not adding, so doesn't matter. If you add also, then no problem. So what is the basically formula? Formula is integration of dV is equal to minus E dot dr. First of all, let's keep the what we know. We know that electric field is KQ small r by capital R cube dot dr. Okay. See, obviously this electric field and dr, that is all thing are correct. So we can directly go to this step KQ by, obviously the angle is 0 degree that we are doing in every question, and this will be d. Now what about the limit? Should I take the limit from again infinity to R, or where I have to take the limit? My question is that where should I have to take the limit? Are you getting my point? I am asking where I should keep the limit. The limit, my limit should be, means my question is that whether my limit should go from infinity to inside point R, or it should go from the center to infinity. Like where I have to see what is the potential. First you tell me, can I directly go from infinity to that point R? Answer is no. Why? Because there is a discontinuity is there. Here the potential will be KQ by small r, but at the surface the potential is KQ by capital R. So we cannot do. Integration is applied for the continuous function. If we have a discontinuity, we cannot apply the integration there. I hope you know this thing. So if it is like this, then what we are going to do? We are going to do one thing, that is we are going to take the limit from inside. We can go like that also, na sir. Then one person will say, sir, we can go from center to R. Okay. If we want to go from center to R, do we know the potential at center? No, it is not 0. Potential at center is not 0. Electric field is 0. That is okay. Electric field at the center is 0. If you now electric field is also not 0. Sorry. Or it is 0. Well, let me check. No. When R, yeah, electric field is inside electric field at center is 0. That is okay. Well, does it mean that potential will be also 0? Answer is no. If electric field is 0, potential will be constant. So we can't say anything. Means there will be some value will be there. Now we have to find that. So we don't know the potential at the center. But one thing is there, we know the potential at the surface. So what we will do, we will go from the surface to that R. That we can do. So we will do one thing. We will try to go from the surface. Means what I am going to do now. I will go from that, from like basically I want to find my VR. So I will go from surface. Surface means surface potential I know. Are you getting my point now? Surface potential I know. So what I will try to do, I will go from point I, means from point R to surface. I will let the potential at some point is VR and potential at surface. Okay, that is my surface point, because surface potential I know. So I will integrate this thing. So it will be minus times of, and or I can do one thing. If I reverse, take this minus sign here, this integration will become potential at a small r minus, because upper limit minus lower limit, that is capital R. Are you okay? Because this thing will be VR capital minus sign will come here, so it will revert. Okay. Now here, now this thing is take everything constant outside. So what is it? I hope you understand the thing what I'm trying to say. We cannot take the we are taking from inside to surface, that we are doing. So R integration will be R square by 2. What is the limit? We are going from inside to surface. So small r to capital R. Are you getting my point? R integration is R square by 2. So that will be K cube by R cube into that will be capital R square minus a small r square by 2. I hope this thing is clear. Now what is the potential at surface? That is K cube by, what is the potential? K cube by R. What is the potential at R? We have to find. This we take common and bring it here. Are you getting my point now? This way will bring it here. So potential at R will be equal to how much? This thing is K cube. Let's take R cube inside and 2 outside. Okay. So let's take R cube inside. So it will become how much? 1 by R, correct? Minus R square by, or we can do one thing better way. Let it be 2R cube into R square minus a small r cube into K cube by R. Now you do one thing. You just take K cube by LCM 2R cube as a common. You will get R square and 2R cube I am taking common. So obviously here we should have a 2R cube. So in numerator we will get 2R square. So from here you will get the potential is K cube by 2R cube into 3R square minus a small r square. That is a potential at R. So what is the potential inside? We will get the potential at K cube by 2R cube into 3R square minus a small s. That is a dangerous form. That is the only thing you have to remember. Okay, that is the formula. Inside the potential will be this much. Okay, it is not a some 0 or something like that. If you want to find the potential at center, keep small r equal to 0. What you will get? You will get 3 by 2 of K cube by R. Means the potential at the center is greater than the potential at the surface. And we know that in the direction of electric field, the potential decreases. So the potential at center is 1.5 times of the potential at the surface. That is the value we are getting from here. So what is the conclusion we have got? So for this, we can write the conclusion like this. So what is the conclusion? I hope conclusion is clear to you. Conclusion is very simple. If it is a solid, non-conducting sphere, okay, so obviously the charge will be on the volume. Okay, the charge will be not took proper. Let me draw it again. Okay, the charge given on this is capital Q. So what is the value we have got? We got that for two cases we have seen here. Two cases we have seen here. What are the two cases we have seen? Sir, we have seen two cases. I am drawing here because I have to draw graph also. So for r less than capital R, sir, and for r greater than capital R, equal to, if you want, I add, that is by r radius. So what is the conclusion we have got, sir? The conclusion is very simple. Here we have find that the electric field formula will be changed. It is kq small r by capital R cube, or you can say this thing will be equal to rho r by 3 epsilon naught. Okay, you can see here kq by small r by capital R cube, rho r by 3 epsilon naught. Okay, clear here? That is the first thing. Second thing is the potential. Potential is at r will be kq. Let me give some space because this is a bigger value. No? Can do one thing. So what is the potential we have got? We have got the potential as, if you remember, kq by 2r cube into 3r square minus small r square. That is the potential we have got. And for r greater than equal to capital R, what is the electric field we have got? That is kq by how much? Kq by small r square. And what is the potential at outside we have got? That is kq by small r. And what is the most important thing? That is the potential at the center. B at center. That is 3 by 2 of kq by capital R. And what is the potential at surface? Surface potential we have got, that is kq by capital R. So what is the diagram we can draw from here? So what is my E vector versus R vector? And then this should be V versus R, and this is my E vector versus R vector. So from here you can say what is the internal electric field? Internal electric field is proportional to, if you remember, it is proportional to R. R is equal to capital R, and then it is decreasing with respect to R. So here the electric field is directly proportional to R, and here the electric field is inversely proportional to R square. Similarly here also, what is the potential for potential case? Can you tell me what is the potential case? At center, what is the potential? At center when R equal to 0, when R is equal to 0, this is 3 by 2 of kq by R. Then after that, when it come to the surface, since R is equal to capital R, what is the potential will become? It is kq by capital R. Then finally it is start decreasing. Okay, so what is the potential here? After that, potential is inversely proportional to small. So that is a graph of E versus V. So there are two cases we have seen. One is combining all the three cases, and the last one we have seen the you have to remember the formula along with the what? The graphs. Note it down, and if you have any doubt, please ask me. I hope it is completed now. Completed. So what we have completely seen the potential, we have completely seen the electric field inside, outside, every point, everywhere we have seen, and there is a no doubt is left there now. Now our next thing we are going to see, that is a potential energy. See, obviously they have a charge, so obviously they will have a some potential energy stored inside it. Now my question is that how much potential energy is stored in them? That is what we have to calculate. So let us calculate the potential energy. Okay. So again, there will be two cases for potential energy also, correct? That is clear to you. Now you are clear, I think so. So for same, we have two cases. First is the potential energy. Again, we have two cases. One case, you know, this is will be either it will be hollow conductor, or either it can be a solid conductor, or either it can be a what? A, a hollow non-conductor. Any of this thing can be possible. So if you are taking these three things, so obviously where will be the charge? The charge will be again on the surface. That is correct. The charge will be on the surface. Okay. So basically how this charge has been bring down here. Basically first what we have did, we have taken the charge. 1 minute. Yeah. So what we have did, basically what we have did, we have, suppose I want to make this system and the radius is fixed. Obviously this is a sphere, radius cannot be changed, radius is obviously fixed because it is a sphere. Now I have to bring the charge and keep on this radius surface, solid cylinder. So radius is fixed. What I am doing, I am taking the charge and bringing from the infinity, I am bringing from the infinity and keeping on the sphere like that. I am bringing the charge from the infinity. So suppose first I bring a small dq charge, first charge. So did I have to do some work? Answer is no, because there is nothing is there, no force is there. Now again I am bringing the another dq charge, so I have to do some work now. Why? Because there will be force of repulsion due to that charge, similar to the potential energy. So there will be some force will be there, so that I have to do some work done. Now what my question is that what is the work done? We know that the change in potential energy is equal to work done by the external agent, correct? This relation, you know, I am very clear because I have given in the earlier only. So this thing will be equal to what? This thing we know, that is dq into v final minus v initial. That is also we know in the when we learn about the potential energy. Now you tell me, at infinity we are bringing the charge now. So at infinity what is the potential we have assumed? We have assumed the infinity potential equal to 0. This is the potential at infinity, correct? Why it is 0? Because it is an infinity point. From infinity we are bringing the charge now. From infinity we are bringing the charge to this point. From infinity, from where? From infinity. So from infinity we are bringing the charge dq. I hope you are clear now. So obviously this thing will be infinity, the potential is 0. What is the final potential when I am bringing the charge here? So it will be k q by how much? Sorry, not capital Q, na? Sorry, small q, whatever the charge at that time, by capital R, because the sphere is fixed. What is this? Is dq. This will be my potential energy. For total potential energy I have to integrate. Now what is the limit for integration? Now you will tell. From where I am bringing the charge? What is the limit of integration? You have to, basically I have to integrate with respect to charge. So initial charge is 0, capital Q. From where I am bringing this? I am bringing from infinity to some point R. Sorry, capital R, no, not R. So basically if you integrate, what you will get? You will get potential energy is equal to, that is k q square by 2. So k capital Q square by 2 R. So basically this amount of energy is stored inside this system, because this is the work done by the external agent. That energy is going to be stored into the system. So if there is a solid, if there is a solid conductor or a hollow non-conductor or a hollow conductor, whatever the case is, that if it has a charge q, then the total energy, or you can say potential energy, which is stored inside it, it is kq square by 2r. That is the thing. And this energy is stored where this energy is stored. My question is that, okay, this energy is stored, so my question is, where this energy has been stored? Where is the energy has been stored? So this energy is stored where? Now my question, are you getting my point? Okay, this energy is stored. Suppose I have plus plate and minus plate. So you tell me that, sir, energy is stored between these two plates. Okay. So similarly here also I am asking, if the energy is stored here also, then can you tell me where this energy will be stored? Are you getting my point? So obviously you can see from the limit, the energy is stored from 0 to, obviously we are bringing from charge from infinity and keeping here, so the energy will stored from here, because the charge is not bounded, so energy will also be not bounded. Okay, so energy is stored from r to infinity. This energy has been stored from r to infinity. Are you getting my point? So this energy is stored from r to infinity, like that. It will radiate like that. It will radiate like that. Okay, so that is the potential energy for this system. Clear? So in this table, if you want, you can add the, in this table, if you want, you can also add, that is my potential energy will be equal to kq square by 2r. It is a for system, it does not belong for r less than greater than, or no, it is for system. This is for system. Similarly, I hope it is clear now. Yeah. Similarly, we have another case, that is solid non conducting pair, and suppose the radius is r, obviously the charge is distributed obviously inside the volume, charge is capital Q. Okay, so here again I will write my potential energy will be equal to how much, that is work done, integration of work done by the external agent, that will be equal to, suppose some dq charge I am bringing from V final minus V initial. Are you getting my point? If there is any doubt, if here, please tell me. Are you getting my point, what I am trying to say? Are you getting or not? Huh? Is it clear? Okay. So another, again the same thing, my V initial will be 0. But here there is a one catch is there. Here the radius will not be fixed. The radius will be also changing. Initially, the radius, suppose at some point the charge on this is Q, because you are bringing, so the radius is also increasing. As you are keeping the charge, the radius is increasing. As you are keeping the charge, the size is increasing. As you are keeping the charge, the size is like that. At suppose at some instant, the radius is a small r and the q is there, and we are bringing the charge dq from infinity. And at some instant, we get at the total charge on this surface we got is q. The charge on this surface we got is q. At some instant, suppose the charge on this surface is q, and we are bringing this charge from infinity. So one thing we can say, this potential will be 0. Now what is the potential at this surface as we are bringing this to surface? So kq, that we know, what is kq by small r. Now the problem is there, if you can't directly integrate. Why? Because sir, here q and r both are what? Both are the variables. So for doing the integration we have to change. Now how will you change? Suppose here we have a rho is given, coulomb per meter cube. So here what is the, here also the rho will be remain same, correct? Rho cannot change. Rho is the fixed property of a material, it won't change. So I can say what? The charge q will be, here can be written as this charge q, okay, will be written as capital Q by or you can say this charge q will be written as, that is rho into 4 by 3 pi small r cube. Now what is dq? Then dq will be how much? dq will be, sir, it is rho sir, rho into, sir, 4 by 3 pi 3 r square, sir, dr. So 3 will cancel out, sir. You will get rho into 4 pi, sir, r square dr. That is the dq value we will get. Okay. And what is q value? This much. So put it here. If you put everything here, q value is rho 4 by 3 pi small r cube by r, and this value, that is dq. dq value is how much? How much is the dq? That is rho rho 4 pi rho 4 pi r square dr. Correct. So a this will be rho square 4 pi square, a rho square 4 pi square by 3. Okay. Then if you will see, the rho square is there, 4 pi square is there. Okay, 3 will come into denominator. This is k, r to the power 5, so r will be cancelled out, so you will get r to the power 6, r to the power 5, correct? 3 to 5 1 4, sorry, r to the power 4 and dr. That is the value you are getting. That is a du. So for total you have to integrate, and the limit will be from how much? From 0 to r. So 0 to r. Let us integrate. Okay, move to the next page. Write it here. Du is equal to a rho square. Tell me if I am writing, I am doing anything wrong. Any calculation mistake if I am doing. 4 pi square r to the power 4, r to the power 4 into dr, na? R to the power 4 r equal to, anything is k into square by square r to the power 5. If you integrate this, what you will get? You will get 15 here in the denominator. Okay, and this will become r to the power 4. Correct? Now let me solve this, simplify this. K is 1 upon 4 pi epsilon naught. This is 15. Correct? What is rho? Rho is capital Q, Q square. What is rho square? That is 4 by 3 2 pi r cube whole square will be there. Then we have 4 will 4 pi into 4 pi into r to the power 4. Are you getting my point? So 3 5 is 50. 4 pi 4 pi 4 pi will cancel out. This I can write it as k q square, then 5. This is r to the power 6 and this is r to the power 4, so r square, and and 1 3 will be left. So that is this thing. What is the finally we are getting? So finally if you will, sorry, finally if you will see, my potential energy I got equal to 3 by 5 k cube square by r square. That is a final potential energy, and this energy is stored from where? This is energy is stored from 0 to r, means it is stored inside. You will see it is stored inside. Raise the energy is bounded, and now we will in the coming chapter we will connect as a capacitor also, because the energy is bounded. You can use anything as a capacitor where the energy is bounded. It is not a good capacitor, but yeah, due to this property we can use it as a what, as a capacitor. So from here we can add, in this case we can add that my potential energy will be how much? 3 by 5 k q square by r. That is the thing. So I hope till here everything is clear. So in this session we have discussed about the conductors, solid and hollow, as well as non-conductor, and every formula which we have given today. It is a very important session for NEET, JEE and JEE advanced point of view. For NEET it is very important session, because for them they are directly, lot of time they have directly asked the formulas and directly the graphs. If you remember the directly the formula and the graph, that is more than enough for them. Okay, so just go through this. In the next session we are going to solve some more questions on this, and then we will proceed further. Okay, till then take care, goodbye. Like it, share it, subscribe it, and have a nice day.